All right, welcome back. Today we finally get an easy one here. What we've been doing is we have been spinning our wheels and walking our way through a series of steps that, quite frankly, nobody is ever really going to use very much. Why did I teach it to you? Because the AP folks are going to ask you about all of those things. So they're going to ask you about bond energies, and they're going to ask you about Hess's law, and they're going to ask you about all of those things. But to be honest, if you were to go and do one of these things in your own life or whatever, you're probably not going to use those techniques very much. Unless you're doing some weird research or something along those lines, you're probably just going to go straight to this idea of heat of formation rather than trying to do some of those other things. You can, and I'm not saying that they're useless, not at all, but I'm saying that if you just want an answer for the heat of a particular reaction, you're probably going to go straight to this method. Again, the AP folks are going to ask you about those other things, so I don't want to discount them, and I had to show you how to do them because you could see them on the AP test. Well, what is heat of formation and why is it better? Well, it's better because we don't have to worry about bond energies anymore. So remember the whole problem that we have with bond energies, you have to draw a Lewis dot structure. What if it doesn't have a Lewis dot structure because it's ionic? Or what if it's a weird Lewis dot structure because it's a resonance? You've got all sorts of things to look at. Then you've got to take the stoichiometry of them into account. No, are they single, double, triple bonds? Are they 1.5? That bond energy thing is really not particularly a convenient way of doing the problems. Hess's law is great. Hess's law, move things around, add them together, get what you want. But then how is that going to work? Are you just going to have a big book of equations? And then how are you going to know which equations to look up so that you can add them together in order to get your overall equation? And quite frankly, if you've just got a big book of equations, why look up a series of equations that you can try to figure out how to add up and get to your overall equations? Why wouldn't you just look up the equation that you want? So again, I'm not saying they're useless, they're not, but if you're just looking for the heat of a reaction, you're probably not going to turn to either of those systems. Well, what are you going to do? Well, we developed this process here called heat of formation. So what is it? Heat of formation, first of all, has a very specific definition that you need to make sure that you know. So heat of formation is you form 1 mole of a substance from its elements in their standard states. So you are forming 1 mole of a substance. You must form it from its elements, and those elements must be in their standard states. So what I'm going to do is I'm going to give you a series of values, these heat of formation values. So if you were to look at something like the heat of formation of acetic acid, right? If you were to look that one up here, or the heat of formation of any of those guys here, what it means is that you are forming, and this is the important bit, you are forming 1 mole from its elements, and those elements have to be in their standard states. So if I look up carbon dioxide here, carbon dioxide has a heat of formation of negative 394, give or take. What that means is that when I look up that value in that table that I just saw, this is the equation that they are saying. Carbon plus oxygen goes to carbon dioxide. 1 mole of an element, you are forming it because it's a product. You are forming 1 mole of it, and you are forming it from its elements, and those elements have to be in their standard states like they would be at normal temperature. So carbon's a solid and oxygen's a gas. You can't have gaseous carbon or you can't have solid oxygen. That doesn't make any sense. So you are forming 1 mole of a substance from its elements in their standard states. So if you are doing the heat of formation of liquid water here it is, negative 286, you can use that number there. And what that number means is that you are forming, there it is, you are forming on the right-hand side, form 1 mole of a substance, and you are forming it from its elements over here, and you are forming it in their standard states. So gas and gas, because hydrogen and oxygen are gas. So you notice I have 1 hydrogen here and only a half of an oxygen because it is forcing you. This system is forcing you to have 1 product. Okay? And the reason is that we want to have this as a per mole basis, so we want it to be for 1 mole of it. Now, these can get awfully complicated. What if I had acetic acid here, HC2H3O2? If I wanted to form 1 mole of that, I would need 2 hydrogens at H2, 1, 2, 3, 4. I would need 2 carbons, C2, there they are, and I would need an O2 because I would need 2 of those. So all of these are their elements. All of those elements are in their standard states, gas, solid, gas, and I am forming 1 mole of whatever it is that I am interested in. Okay? Now again, the reason that we can do this is that the heat of formation of elements then is going to be no change. So for example, if I wanted to form 1 mole of oxygen and I wanted to form it from itself, well then there's going to be no energy associated with those elements because it's itself. There's no change. And so what we are doing is we are establishing that the heat of formation of elements is 0. Take a look at carbon. If I want to make 1 carbon and I'm going to make it from 1 carbon, well then there's no change there, nothing happens. So the heat of formation of carbon is 0 there. So here's why this is useful to us. We can then put together a bunch of chemicals. Let's take a look at this guy here. So if we then get out a calorimeter and we go through and we design an experiment, and in our experiment we take 1 mole of carbon and we take 1 mole of oxygen and we make 1 mole of carbon dioxide, and I calculate the delta H of this reaction. And I calculate the delta H through our calorimetry and enthalpy means, and I determine that the delta H of this reaction is negative 394 kilojoules, right? Well, this is an element in its standard state. It's 0. This is an element in its standard state. It's 0. So everything on the left-hand side over here is a value of 0. And so consequently, I can take this negative 394 and say, well, if everything over here is a 0, then that 394 is going to be just for my carbon dioxide. So I can then go down here and put it in a table and say carbon dioxide has a value of negative 394 relative to making it from its elements in their standard states. So I do another experiment. And in my second experiment, I make 1 mole of liquid water, and I make it from 1 mole of hydrogen and half a mole of oxygen in their standard states. Well, that has a value of 0 because it's an element in its standard state. That has a value of 0 because it's an element in its standard state. And so, consequently, whatever delta H happens when I go to do this experiment, negative 286 by the way, I know that that negative 286 is the value for liquid water, because if this is a value of 0 and this is a value of 0, then the negative 286 must be for the value of this guy over here because the other ones are zeros. And so that's how we do this system. We are going to assume that elements have a standard heat of formation of 0. Elements in their standard states have a heat of formation of 0. And you'll see that in tables, although they don't even have to give it to you, but they often do. So here's liquid bromine. It has a heat of formation of 0. Here is gaseous chlorine. 1 mole of it, it's an element. That's how it exists in nature, and it's in its standard state. Here is iron. It's a solid because under normal conditions, iron is a solid, and it has values of 0. Here's hydrogen. It has a value of 0. Elements in their standard states have heats of formation equal to 0. Now, here's the best part about this. I said this was easy, and it is. Because all of these things, all of these substances have heats of formation, these elements of 0 over here. I can now combine this with my Hess's law idea that if this substance is over here on the right-hand side, then I'm going to leave the delta H exactly as it is. But were I to flip this over here, then what would happen? Well, I would have to take the opposite side of that, opposite sign of that, because again, if I flip an equation around, I have to take the opposite sign of things. So if you combine Hess's law with our idea of heat of formation, you get this very simple equation. And this is the one that's going to be most useful to you in all of this. The heat of the reaction is going to be equal to the sum of the heats of formation of the products minus the sum of the heats of formation of reactants. And that's how just about every equation that we're going to use from now until the end of the unit is going to work. It's going to be your final products minus your initial reactants over here. Now, for complete disclosure, this looks very similar to the one that we did for the bond energies. Remember the bonds? The bonds is the same equation, but it's reversed. The bonds is the sum of the bonds of the reactants minus the sum of the bonds of the products because of the way that system is enforced. So please just note that when you do the bonds, it's reactants minus products. When you do it the easy way, it's what you would expect the delta to be, final minus initial. So all you have to do is add up the heats of formation of the products and subtract the heats of formations of the reactants. Let's take a look at this in action. So what have I got? I've got this equation here, right? So I have been given all of these heats of formation. Well, first of all, the nitrogen is a 0 because it's an element in its standard state. So that I don't have to worry about. The oxygen is also a 0 because it's an element in its standard state. I didn't even have to give you those, but I did. So if they don't give you a number, it's either because they want you to calculate that number or they don't need to because it's an element in its standard state and therefore it has a value of 0. So what have I got here? I've got two waters on the right-hand side. So it's products minus reactants. So what are my products? My delta H of my reaction is going to be the sum of the products. We'll start there. I've got two waters on the right-hand side, the products side. Well, water is negative 242 as a gas. So don't forget that there's two of them, so that's going to be 2 times negative 242. So that's my products, P. And then I'm going to subtract my reactants. What do I have for reactants? I have 1 of this ammonium nitrate here. So I'm going to subtract from that negative 366. So I've got two negative 242s, and I'm going to subtract the negative 366. So 242 negative twice, and then I'm going to end up adding the 366 because I'm subtracting a negative. So I end up with a negative 118 as the delta H of my reaction, negative 118 kilojoules per mole. See how easy that is? Products minus reactants, and you move on with life. All right, sample 2. What if I take this and I want to know the delta H for the reaction? Again, I could go through and I could figure out the bond energies of all of this stuff, or I could figure out other equations and reverse them together and add them up and get, no, or I just do products minus reactants. I just go to a book, I look up these values in a table, and I add up the products and I subtract the reactants and I move on with my life. So what is my delta H here? Well, it's going to be equal to products, 6 carbon dioxides. So that's going to be 6 at negative 394 here. Okay, so that's my carbon dioxides. And then I'm going to need to add to that 3 waters. So that's going to be 3 at negative 286. So that's everything on my products side here. All right, that's everything on my products side. I got all that now. And then I have to subtract everything that's on the reactants side over here. So I'm going to subtract then a benzene, a liquid benzene here. So I'm going to subtract a 49. And then I'm going to subtract 7.5 oxygens. Oh, wait, it's 0 because it's an element in its standard state. So all I have to do is subtract 49 from that. So what have I got? I've got 394 negative 6 times. Like so, and then a 286 and another 286 and another 286 that I'm adding the negative values of. So that's negative 3222, and then I'm going to subtract 49 from that, and I get negative 3271. So my delta H for this is negative 3271 kilojoules per mole. So that's how easy this process is. You add up the products, you subtract the reactants, and you're done. You don't have to worry about bond energies. You don't have to worry about adding or subtracting equations or anything. You just add up the products, subtract the reactants.